When considering the algebraic operations on vectors and matrices, it's important to keep in mind what properties they satisfy. Matrix multiplication is not commutative, but it is associative. Multiplication always distributes over addition, whether you're multiplying vectors, matrices, or scalars. The notion of a null vector, a null matrix, and the identity matrix. Then there are several useful geometric notions associated to vectors and matrices. An n-dimensional vector, or a vector with n coordinates, can be thought of as an arrow pointing from the origin to a point in r to the n in real n-dimensional space. More generally, given 2 points in real n-dimensional space, a and b, one can take an arrow pointing from a to b to define a vector. It's usually written like this. The coordinates of this vector are the coordinates of the point b minus the coordinates of the point a. There are lots of geometric interpretations to rules for vector addition and taking scalar or dot products. You should be familiar with the parallelogram rule. Thinking about vectors as arrows between points in real n-dimensional space, one has a natural notion of the length of a vector, or the norm of a vector, which algebraically is given by this formula. One takes the dot product of the vector and itself and takes the square root of that. Or more precisely, it's the dot product of the transpose of the vector and itself. There's also a natural notion of an angle between two vectors. One defines the angle cosine theta as the dot product between two vectors x and y divided by the norms of x and the norm of y. If these are vectors in 2 or 3 dimensions, there's a natural intuitive notion of length and angle, and you can picture it in your head. But these concepts really make sense in any dimension. Given 2 vectors, 2 lines pointing from the origin out to a point, in a space of any dimension, there is a unique plane that contains those 2 lines. And then one can think about the angle between the vectors as the angle in this plane. These geometric ideas also extend to matrices that act on vectors. And so you should be familiar with the basic notions of scaling, of rotation, reflection, and projection as geometric operations corresponding to multiplication by matrices. I think that's it. I have no idea what comes next.